Testing on YouTube. Testing on YouTube. Testing on YouTube. Testing on YouTube. All right, YouTube seems to work. Twitch is not working for some reason. I think Twitch is dead. Whatever, we'll go without Twitch. We'll do it live. All right, now we just need X. How's it going, Nisio? How's it going, Mosin? How's it going, Blessings of Allah? What a crazy name. All right. Almost about to get started here. Just a minute until X goes live, and then we'll get started. All right, I think it's live. All right, we're live on all the different platforms, so let's go ahead and get this started. All right, welcome to another Hoopo stream. We've changed the streaming time. We're now streaming at 10 a.m. instead of 8 a.m. See if we get a slightly different crowd of people. So we're going to be talking about some kind of over talked about news. If you've been on the internet at all the past couple days, everybody's been talking about Gemini and Sora. So we're going to try to maybe talk about things that people aren't talking about related to these, and we're going to try to compare them. And they're not really models that you can directly compare. They're kind of doing different things, but we're almost going to compare them in terms of like which one is the most extraordinary. You know, maybe you think about it that way. So going Kaz-Ax. Apparently I know who Blessing of Allah is, but I don't know who that is. I swear I don't know this guy. All right, so there's the two papers that we're going to be talking about, and they're not even really papers, but it's going to be Sora. Sora is basically the new state-of-the-art video generation model. This comes from OpenAI, and of course they didn't release a paper because they're closed AI, but they released what they call a technical report, which is kind of like a weird little blog post that has some references and then has a bunch of videos for you to watch. And I'm sure you've seen these videos time and time again on Twitter and YouTube and all the different reaction videos to these videos, so we're probably not going to spend too much time just looking at those videos. The other paper we're going to be looking at, and this one actually is a paper, but in a lot of ways it's not a paper. This one's Gemini 1.5. This is Google DeepMind, unlocking multimodal understanding across millions of tokens of context. So the story around how these were released was a little bit weird. So Google released Gemini 1.5, and then almost immediately, like a couple hours later, OpenAI released this one. So the timing of that makes me think that they were waiting to release this. So basically, Sam Altman, like one of the things he knows how to do very well is kind of manage hype and control the narrative. So he basically was like, let's wait to release this. If we wait until Google releases their kind of big thing and then we just kind of steal their thunder with this, it'll put us in a better position than Google. So that's kind of my conspiracy theory around the timing of these. But we're going to dive into these and kind of explore technically what might be going on behind these, because the reason that I don't really want to call these papers is that they don't really tell you what's going on here, right? It's like there's kind of, unfortunately, AI has become a secretive kind of internal thing where people kind of basically do everything internally. They don't really release papers about it. They don't really tell you what's going on. They give you kind of these generic high-level ideas, but this is not really telling me much. It's just kind of a super high level, like, oh, we do things. And most importantly, they don't tell you the data sets. So neither of these papers give you any idea as to what the data is that they've been trained on, what the mix of the data is, what the training recipe is, how they're cleaning the data, how they're potentially augmenting the data, recaptioning the data. There's so many different things that have to do with the actual data, which to me is the most important part of any of this, right? The data is the most important part when it comes to a machine learning model. So it's kind of really suspicious that nobody wants to talk about the data when the data is really all there is to do. So maybe let's start with this. So is Sora state of the art? Can we verify that claim? And I think pretty comfortably we can say yes. So for one, it generates a lot longer videos, right? So you can see obviously this video is way longer. Down here you have a couple different competitors using the same kind of prompt, but it's still not necessarily perfect. You can see obviously there's sizing issues here, like this family appears to be giants. This stuff in the background doesn't necessarily make sense from a perspective background, but the amount of motion in the video, the length of the video, and the overall quality of the motion seems a little bit higher. So just from that, I feel like I'm comfortable saying this is state of the art. Okay, so now that we've kind of proved that it's state of the art video model, why is everybody so hyped about this, right? Is it just we're going to see better TikToks with slightly better video? Not quite. I think one of the big kind of sleeper reasons why people are hyped about this is that this level of quality for video generation represents kind of the a step function at which point you can start potentially using this for 3D generative stuff. So if you've watched any of my previous streams, one of the things we talk about a lot is basically generative 3D. And in generative 3D, which is kind of like text to image, except now imagine text to a Gaussian splat or text to nerf or something like that, where you're generating 3D content. One of the things that pretty much everybody does is they use Stable Diffusion. They use pre-trained text-to-image models in order to basically extract the intelligence that you need in order to actually create a generative text-to-3D model. So this new text-to-video model from OpenAI, people have already been kind of putting these into, I think this is like some kind of Gaussian splat or nerf website where you can kind of create, you see this little point cloud, which is done using kind of structure from motion, but you can see it's pretty good, which means that we can expect a step function improvement in text to 3D and generative 3D stuff within probably 6 months. So that's kind of the other reason people are hyped. It's not just the quality and this stuff that the 2D content that people are going to be creating with this, but it's also the 3D content that people are going to be creating with this. Okay, so who's responsible? So this is the original tweet by Sam Altman, who is the CEO of OpenAI. And he personally calls out these three people here. So Tim Brooks, Bill Peeb, and Model Mechanic. So who the fuck is Tim Brooks? Tim Brooks is this guy. Tim Brooks is a research scientist at OpenAI, but previously he was a University of California, Berkeley PhD. So this is his PhD thesis right here, right? Single author, huge ass paper where generative models for image and long video synthesis. So that's this guy. And what he's really known for, and this is the reason he was probably hired by OpenAI, is this paper here, right? So if you actually go to his Google Scholar, the most cited work he has is this Instruct Pix-to-Pix, published in 2023, the year he became a research scientist at OpenAI. So it's kind of, you put two and two together. That's the reason he got hired. And this is Instruct Pix-to-Pix, learning to follow image editing instructions. You see his name there at the front. So the name at the front is the person who did all the work. The name at the back is the kind of senior person, the like advisor, professor type. But if you're hiring for a startup and you want someone that can actually code and actually do things, you hire the guy at the first name in the paper, right? That's the guy that you want to hire. Okay. So in this paper, they basically create a diffusion model that allows editing images. So basically you can see here, it starts with an image, you add some text here, turn it to a still from a Western, and it adapts it. And we actually did do a stream on this. I think it's been a while ago, but you can check the streams for that, but it's a relatively simple idea. And here is figure 2, and this basically tells you what this idea is. So first thing you do is you're going to basically generate a data set. And the way you generate that data set is you start with a caption, so a photograph of a girl riding a horse, and then you use a language model such as GPT-3 to basically create, have her ride a dragon, and then edit it into photograph of a girl riding a dragon. So you've gone from a single caption into now 2 different captions, one that says photograph of a girl riding a horse and one that says photograph of a girl riding a dragon. You feed both of those into Stable Diffusion, and you're going to get basically 2 different images. So the way that you get both of these images to look like they're quite similar is basically this prompt-to-prompt idea, which is some combination of using the same starting noise and some other little trick that they have here. But ultimately, you basically get these kind of paired matching images with different prompts. And then now that you have the different prompts and the paired matching images, you can effectively create these training examples, which is the data set that you're going to train this instruct pick-to-picks, right? So, for example, here, have her ride a dragon, and you use those 2 images that came out of Stable Diffusion. So the main kind of idea and technique behind instruct picks-to-picks is basically using Stable Diffusion as a generator and GPT-3 as basically a prompt engineer, I guess, that basically creates variants of prompts. And once you have that data set, then you can, I don't even know if they've trained this from scratch. They probably just fine-tune an existing pre-trained diffusion model, aka Stable Diffusion, but then you get the ability to, given an image and a prompt, change it to a new image. And that's basically what this Tim Brooks guy is known for. So that's one of the 3 people that Sam Altman calls out. Who's this next person that Sam Altman calls out? So this next guy is Bill Peeb. So if we actually go, this is Bill Peebs here. Bill Peebles, by the way, that's a badass name. You know, Mr. Peebles. In fact, it's probably not even Mr. Peebles. It's probably Dr. Peebles. So sit your ass down when you're talking to Dr. Peebles. But this guy works at OpenAI as well. And if we look up this guy, he's got a nice little website. His name is actually William Peebles. He calls himself Bill, apparently. But research scientist at OpenAI, also a Berkeley PhD. So 2 Berkeley PhDs. And this guy is known for his work, specifically this one here. I don't know if I can see it here, but Jan LeCun calls this guy out. So Jan LeCun is the kind of like the Meta chief AI guy, even though he's not really the chief AI guy at Meta. He's kind of has a more of a ceremonial role at Meta. But he says the diffusion transformer paper is done by this guy here, signing Xie, and then William Peebles, aka Bill Peebles. And he's referring to this paper here. So this paper here, Scalable Diffusion Models with Transformers by our dearest William Peebles, and then signing Xie, who's the other guy here, who's now at Meta, I guess, or like some kind of assistant professor, visiting professor kind of situation going on. But what is that? Basically, this is another generative model in the image space, but it uses a transformer. And what exactly means that? So we explore a new class of diffusion models based on the transformer architect. We train latent diffusion models of images, replacing the commonly used UNet backbone with a transformer that operates on latent patches. Okay, so that's a little bit of a mouthful, but what exactly is going on? So what they're referring to here is a latent diffusion model. A latent diffusion model is what Stable Diffusion is. Stable Diffusion is a generative image model that it's denoising images in the latent space. So the latent space is this little multicolored little thumbnail here. What it's referring to is basically an autoencoder. An autoencoder, what it is, it's 2 models. There's what's known as the encoder and the decoder. And the encoder and the decoder, let me see, I have one pulled up, but the encoder and the decoder are trained basically to reconstruct. So you can see here, if you feed this image of the number 4 into an encoder, it crushes it down into this little vector otherwise known as a low-dimensional representation, an embedding, a feature, whatever you want to call it. And then the decoder is going to consume this little crushed, little low, small, little vector, and then it's going to try to reconstruct the input. And people have trained these types of autoencoders on images. And when you autoencode, or when you encode an image, you end up with this little, what's called a latent image, or this little thumbnail. And why do people even do this? Well, because this is much smaller, because this Z0 here is a lot smaller, a lot easier to deal with than the full image. So that's what people do. That's why people use latent diffusion models and not image space diffusion models. But the important part of this that I wanted to show you guys is this part here. So once you actually have an encoded image, then you basically are denoising it through a bunch of steps. So here you have a repeat T times. So it's iteratively removing noise for T steps, or T can be discretized however you want, right? But normally the model architecture that people use for that is what's called a U-net. A U-net is basically kind of like a convolutional neural net that goes from being very wide, then to being narrow, then to being very wide, right? So it's kind of like a convnet. So Peebles, our good old friend Dr. Peebles here, he's known for this paper here, Scalable Diffusion Models, which basically replaces the U-net backbone with a transformer. Okay. So if we actually look at it, here it is if you really want to see it. So this is what a DIT block looks like. And the DIT block is basically a diffusion transformer, diffusion T for transformer, and it basically just replaces this part of the latent diffusion model. So that's what our good friend Peebles is known for. All right, so you guys are absolutely blowing up this chat. Let me see if I can pause here for a second. Thanks for the 10, Patrick Olden. How cherry-picked do you think the examples in the Sora page are? A little bit cherry-picked, but not like egregiously cherry-picked. So everything is a little bit cherry-picked, but I don't think they went through like 10 million or like 1,000 of these and then picked the best ones, right? They probably went through like a dozen and then picked out of that dozen and then sent it to a safety guy, and then the safety guy was like, yeah, don't show this one because this is a white person, show this one because this person's Asian, right? Like that's probably how they ended up on this one. Launch, this turns out pretty good to be true. Okay. 3D models. Jimmy Apple said they have had Sora since March last year. Yeah, I think they were sitting on this. I don't know if they had it since March. That seems like a long time because this Tim Brooks guy, he didn't even get hired. Like if you look at, let's do this, Tim Brooks LinkedIn. Oh, not now. I'm opening this on secret, but, oh no, I have to sign in. But I don't even think he was at LinkedIn or at OpenAI in March, so March seems a little bit early. I don't know about that. Text to 3D. How's it going, Ed? How's it going, Majetti? Okay. Any other questions here? Berkeley folks going ham. Yeah, Berkeley is pretty good. You know, it's right by San Francisco, so it's kind of like there's a feeder pipeline from Stanford and Berkeley into the startups and companies in the Bay Area. Thanks for the... I don't know what those are. Supports? Money? Thanks for the money, Majetti, I guess. Is latent image lossless compression? Questioned by 87G, and it is not. So any kind of autoencoder, variational autoencoder, or quantized VQ, VAE, so those are all types of autoencoders, they're lossy. So you're going to lose some information when you do this, and your reconstruction is never going to be perfectly what you had at the input. But you're training using a reconstruction loss, so over time, this encoder and this decoder are going to get better and better and better and better. The encoder better at basically compressing all the important information into this latent, and then the decoder better and better and better at reconstructing a good-looking input from the latent. So it's a lossy form of compression, but it's not... It's pretty good, I guess is what I'm saying. All right. So we've looked at Peebles, we've looked at Tim, and now let's look at the last person. So the last person that he mentions is Model Mechanic. Model Mechanic is actually a guy called Aditya Ramesh. Aditya Ramesh, if we look at his publications, he's got 21 papers here, a lot more citations here, so 14.5K citations compared to, for example, just 1,000 for Tim Brooks. Makes sense, Tim Brooks a little bit younger. I think this guy is probably a little bit older, so this guy's probably the more senior person. You see he's got some articles on language models, and then here you go. Here's some papers that he has on image stuff, hierarchical text conditioned image generation with clip latents, zero-shot text image generation, learning transferable visual models from natural language supervision. So he's got an image is worth 16 by 16 words. So a couple different papers there. So let's look at some of these papers. So this is Aditya Ramesh. So obviously right off the bat, you see that he's in the first slot there. So even though Ilya's on this paper, Ilya probably didn't do any of the work here, right? Ilya is like on the legacy advisor slot. Like he just basically sat in the meetings and said, yeah, this looks good to me. Aditya, he's the guy doing the work. So far, right, you've noticed that the three people that Sam Altman calls out, if you go to all their papers, they're always in the first. They're the first name, Tim Brooks. See that? William Peebles. See that? Aditya Ramesh. So these are the people that these are the builders. You know, these are the guys who actually do the work in these papers, which is the type of people that OpenAI wants to hire, right? They want to hire the first couple names. They don't really want to hire the last name because the guy here is going to be way more expensive to hire than the guy here. But the guy here actually knows how to do the work versus the guy here hasn't coded since like the early 2000s, you know? Okay, but this paper, what is it? It's basically just a generic kind of text-to-image paper, transformer that autoregressively models the image and text as tokens in a single stream of data. Also uses a variational autoencoder, in this case, a discrete variational autoencoder. So what is meant by a discrete variational autoencoder? Let's pull up this one, our autoencoder. So a discrete autoencoder or a vector quantized autoencoder, there's a bunch of different types, basically is where this bottleneck here isn't allowed to be basically some arbitrary vector where the values are like 1.0001 and 0.74374, right? In a discrete autoencoder, the bottleneck here is basically limited to some discrete set or number of vectors, right? It's often called a code book, but it's basically a way to discretize this space here. Okay, the other thing I wanted to point out in this paper is this idea of image tokens. So this is going to bring us back to the technical report. So turning visual data into patches. Okay, so LLMs use tokens. We consider how visual data can inherit. Sora uses visual patches, blah, blah, blah. They're kind of making it seem like they made this up, but people are like, this is ancient. You know, like visual patches and vision transformers have been used for a long time. They're definitely not the first people to do this. And if you don't know what a vision or a patch is or a visual token is, this is the kind of easiest way to describe it. So you have an image, which is two-dimensional, or it's actually three-dimensional because you have the height and the width, but then you also have the channel dimension. So in raw image space, it's RGB, but in a latent space like this, you also have height and width, but then you also have the channel dimension or the feature dimension would be much bigger. So it'd be maybe 128 or something like that. So an image patch, or patchifying the image, is taking an image and then cutting it into basically these little patches and then feeding each of those little patches into a transformer. This is kind of a standard transformer block here. You've got your normalizations, you got your self-attention, and then you got your feed forward or your multi-layer perceptron. And why do we need to do this? Why are we cutting up this image into these little patches and then feeding in these patches? Because a transformer, the transformer model architecture assumes a sequence. So in order to feed something into a transformer, it needs to be a sequence of things. So it basically needs to be a ordered list of things that are like, here's thing 1, here's thing 2, here's thing 3, here's thing 4, here's thing 5, and so on, right? So you can't feed a two-dimensional thing into a transformer. It needs to be one-dimensional. So in order to make it one-dimensional, we basically do this left to right, top to down, and then feed it into this transformer blocks, such as here. And then we also add what's known as position embeddings, which are little extra information here that lets the transformer know kind of where in the image, or in a language transformer, where in the sentence the individual patch came from. So that's what they mean by these patches. So anytime they talk about visual patches, what they're talking about is literally that. It's basically cut up little chunks of the image, and then here you can look at them and they look like a little cut up chunk of an image, but as soon as you linearly project them and then feed them through multiple layers of a transformer, they're not going to look like this anymore, right? They're basically going to be some little vector of completely ununderstandable numbers that as a human you have no idea what the fuck it is, but it's kind of the same thing as a text token, right? It's just some black box vector that represents some little chunk of an image rather than a little chunk of a word, which is what a text token is. Okay. So at a high level, we turn videos into patches by first compressing videos into a lower dimensional latent space, aka these little patches, which are smaller, and subsequently decomposing the representation into space-time patches. So this is another interesting, like, this is kind of the state of like AI research where like they don't actually tell you what they're doing, so we have to basically infer what they're doing and like guess and like kind of sit there and like read the tea leaves and like figure out what exactly is going on. We train a network that reduces the dimensionality of visual data. This network takes raw video as input and outputs a latent representation that is compressed both temporally and spatially. Okay, and then they train a decoder that maps generated latents back into pixel space. Okay, so you see the way that they're saying train a decoder and the way that they're saying train a video, train a encoder. So that to me tells me something, right? And if we actually go back to this Jan LeCun post, he mentions this Signing Xie post. Signing Xie is this guy, the guy who wrote the scalable diffusion paper, the DIT architecture that replaces the UNet, right? But the way that this stuff is worded, I think that they not only replaced the UNet, I think they also trained new encoders and decoders, right? So actually, here he says, looks like it's just a VAE, but trained on raw video data. Tokenization probably plays a significant role. VAE is a ConvNet, so DIT is technically a hybrid model. I don't know if I agree with this. I think that what they might have done is they might have trained a new encoder and decoder that is basically like this DIT, but rather than this DIT, which is consuming patches of images like this, where is it? Like this. I think that they did something along the lines of this. So this is another paper that came out recently, and we did do a stream on this one as well. This is the 23rd January 2024. This is called Lumiere, a space-time diffusion model for video generation. This, for a brief moment, this was the state-of-the-art video generation model until, and we even predicted it on stream. On stream, we were like, there's no way this is going to be the state-of-the-art video model for too long. It's probably going to get usurped pretty quickly. But in this paper, they basically treat the space and the time dimensions such that they can create one model that generates the entire video in one shot, right? So what exactly is going on here? So basically they create this space-time UNet, and the space-time UNet, if we go here, treats a video as basically, rather than just one image that has height and width, now they also add this T dimension here, right? So this isn't exactly what's going on here, right? This is a UNet which replaces the UNet, much like this DIT replaces the UNet. But I think you could do something similar to this, where you basically create a autoencoder, variational autoencoder, that is based on something like the DIT, but that rather than patchifying and encoding image by image, right, in a video, which is what pretty much everybody else does. I think it encodes the entire video in one go, right? And that's how you get this space-time latent patches. We extract a sequence of space-time patches. So I think the fact that they keep using this word space-time, the fact that they said they train a decoder rather than just using some other pre-trained decoder encoder, that to me kind of feels like they probably trained their own encoder decoder that consumes an entire video rather than just images like this. And that encoder decoder that they trained is probably something like this DIT, right? But rather than just a DIT that basically consumes a bunch of images like this as a sequence of image tokens, it consumes a sequence of images or a video and then turns it into a sequence of space-time patches. So that's my theory. Again, I don't know. I'm not in contact with these people. They aren't really explaining what they're doing. So we're just kind of like hypothesizing what they're doing. And also, part of my reasoning for that is that this is pretty good, right? This is state of the art by a margin, right? So like it's not, I don't think they just took a pre-trained VAE and then they took Stable Diffusion and then just fine-tuned it a little bit, right? I think they did a couple things from scratch, and that's why you're able to get this state-of-the-art stuff. So that's kind of my theory around that. This is another one of Aditya Ramesh's papers. Is there anything here? No, I don't think there's anything here I wanted to talk about. Okay. That's pretty much it. And yeah, I think this is the paper that people are not paying enough attention to. This is the Lumiere paper from Google, which I think is a lot of the ideas that are coming out. And this paper, like I said, when it actually came out, it was state-of-the-art text-to-video generation. So I suspect there's something similar to this going on in the OpenAI Sora. Our patch-based representation enables Sora to train on videos and images of variable resolutions. So why can you do that? Well, because once you turn an image into a sequence of patches, then it doesn't matter, right? Once you turn an image into this flat sequence of patches, the image size doesn't really matter. The length of the video doesn't really matter because it's the same way that any autoregressive transformer can consume an arbitrary paragraph of any length, right? Well, obviously there's a context length eventually, but you could feed it 2 sentences and you could feed it 10 sentences. So it's robust to that. And the same way here, right, you can, because you're patchifying this video into these space-time tokens, you can feed a very wide resolution video that is only 4 seconds long, and then you could also feed it a vertical video that is 60 seconds long, right? Because both of those are just going to be turned into this sequence of patches. We can control the size of generated videos by arranging randomly initialized patches in an appropriately sized grid. So here what they're talking about is that once you actually want to generate the video, right, what you're going to be doing is denoising it. So you're going to denoise that. And when you denoise in a denoising diffusion model, you start from noise. Actually, this is not a good picture. Let's do diffusion noise. I want this picture. Yeah. So whenever you're doing a diffusion model, let's open this in a new image. Open a new tab. So you start from noise, and then what the model is doing is it's predicting the noise, and then you remove that noise, and then you do that a bunch of times, a bunch of steps in a row. Each of these is an inference step, and you end up with the image. So the size of your noise here ultimately determines the size of your data. So you can control the size of the generated videos by arranging randomly initialized patches, where here, this is a diffusion happening in the image space. Normally the diffusion happens in this latent space, but since your latent space is just a sequence of patches, you just initialize a bunch of random patches and then denoise those patches and then eventually decode it into the video. Okay. Given noisy input, trained to predict original clean patches. So that's this, right? This is the clean patch. This is the noisy patch. remarkable scaling properties, transformers scale effectively, diffusion transformers scale effectively as video models. Sample quality improves as training compute increases, which that's the other kind of thing here, right? It's like, why are the state-of-the-art video models coming out of DeepMind papers with 20 people on the list and then OpenAI papers? It's because they have all the compute and they have all the data. So it's not that they're necessarily smarter than you and they're coming up with some model architecture that you couldn't think of, because that is the case, because they literally are smarter than you, right? These Berkeley PhDs are better at making model architectures than you are, but that's only like 10% of the reason why they're getting state-of-the-art, right? The main reason they're getting state-of-the-art is because these guys have a bigger GPU budget than anybody, and they probably also have much bigger data sets than anybody. Because we know that one thing that they're doing is that they basically do this kind of data augmentation where they take leverage GPT to turn short user prompts into longer detailed captions that are sent to the video model. So basically, rather than training on a caption data set where you have like one image and one prompt, where the prompt is quite short, such as a photograph of a girl riding a dragon, and there you go, it's a girl riding a dragon, they'll feed this image into a vision language model such as GPT-4V, and then they'll use a language model to then further kind of augment this caption. So basically, you'll feed this into GPT and you say, okay, give me this caption, but like a lot more detailed. Make it like 3 paragraphs rather than just 1 sentence, right? So I call this like augmentation, a type of data augmentation, but I think the word that people normally use now is called recaptioning. But this trick of using longer detailed captions by using GPT or some kind of VLM is quite popular. So videos generated, okay. Another thing that people talked about that might not be true is that they used Unreal Engine to generate synthetic data for this. So I'm in the unique position where I actually literally made synthetic data generators using game engines. I didn't use Unreal Engine, I used Unity, and this was some years ago. But having done that myself, I feel like I'm fairly comfortable that they probably did not do that. So let me clarify that. So do I think that they used some video game videos in the training data? Yes, for sure. For sure that these guys are scraping every single possible piece of video data on the internet, right? So for sure, they eventually were like, hey, we found this random streaming website where there's people that stream video games and there's like literally 10 billion hours of videos on here, but it's all video games stuff. And they were like, fuck it, put it in there. We'll train on it, right? That's what I think they did. Why do I say that? Because generating your own Unreal Engine synthetic data requires a completely different kind of skill set, right? These guys don't know how to do that. Tim Brooks, these guys, Bill Peebles, like they don't know how to make Unreal Engine games, right? If you're doing that kind of synthetic data generation, which is the type of synthetic data generation that I did in my startup, you need to hire like game developers and asset artists and all these different kinds of skill sets that I just don't think OpenAI is doing. So that's my take on the whole synthetic data side of this, is that I don't think OpenAI itself explicitly generated Unreal Engine synthetic data for this. I just think that sometimes you see like kind of video game looking type artifacts, like people were talking about the smoke that's coming out of this car and like the way that it bounces. It's very reminiscent of a video game. And surely that must mean that OpenAI is generating their own synthetic data. I think the real answer is they just trained on video game videos, right? Like videos of people playing video games. So there's some portion of the data that this is trained on that comes from video games, which is why you see the kind of video game artifacts. But I think they just scraped that from the internet. I don't think they actually generated that in-house, just because the skill set of the people required to do that is just too weird and too kind of left field for OpenAI to do that. So that's my take on that. Simulating digital worlds. I think this is the Actually, let me pause before I go into that discussion. Patch is like a token. What is a space-time patch? All frames of the video broken down into patches and concatenated? Yeah, basically that. Space-time patch would basically be this, but you do it for every single frame of the video, right? So basically similar to what they did here with the space-time diffusion model, where they basically create this space-time unit that consumes not just the height, not the width, not the channels, but then also this time dimension. So just imagine this, but having also the time dimension. So you basically have this super long sequence of patches. 2D plus time. They bought that Minecraft clone and they're making agents for that. They may have a few game devs in-house. Yeah, maybe. I don't know. My suspicion is that I think they're just using video game data, but they're not like making their own synthetic data stuff, just because that's like a whole different startup. But yeah, used free assets from Unreal Engine. That's probably what they did. Okay. All right. So the other kind of thing that people have been talking about with this is and it's the name of this like little technical report here, is this world simulators. So people have been trying to kind of say that this thing is like a simulation engine or something like that. Like it basically is simulating the real world. Yes, but no, right? I think it comes down to like the use of that word simulation. Simulation doesn't have like a very specific definition. It's a very broad kind of thing. So like, is there some world understanding here in this model? Yes. Is there enough world understanding to do like high level physics here or like physics simulations? No. You know, like, I feel like we're eventually going to move there, right? Eventually you're going to, and I think this stuff kind of shows that we're moving in that direction, right? You're seeing how, yes, the 3D geometry of this stuff is good enough that you'll be able to use this for 3D stuff. Like I expect there to be a lot of 3D generative work that uses Sora as its kind of like source of intelligence, the same way that all the 3D generative work nowadays uses Stable Diffusion as the intelligence. But I don't think we're quite at the point where you can call this like a world simulator, just because there's a lot of weirdness that happens. So one kind of thing that someone pointed out, which is worth showing here. So one of the viewers on our channel noticed one of the weird little flickers. So here around the 14-second mark, the legs flip. So if you look at these legs here, so if you look at her legs, right around 14 seconds, the legs are going to do something extremely weird. Watch this. Wait for it. Oh, you see that? You see that? See that weirdness right there? You see how her legs just kind of like flip on themselves? Let's see that again. So we're going to move it back to 14. Boom. You see that? Okay, so, and I think there was also some other thing I saw on Twitter. I don't have it pulled up, but basically the perspective is all wrong here. So like if you were to actually put like vanishing line points and kind of like classic perspective geometry that you would use if you were actually trying to draw this right with a pencil and paper, there's still a bunch of stuff wrong, but we're getting there. We're getting there. I think people are just getting a little bit too excited too quickly. But yeah, you'll definitely see people use this in robotics. You'll see people use this in 3D stuff. Okay, and that's pretty much all I have for Sora. I think it's pretty good. Definitely state of the art. You know, they got some smart people working on it. From what we can deduce, it's basically a latent diffusion model. The diffusion is happening in this latent space-time patches, which is likely some kind of transformer-based autoencoder that kind of encodes the entire video at once. Because another thing that they say here is that the entire video is generated in one shot, which I've only ever seen in this paper, right? So this is the only paper I've seen where you basically generate the entire video in one shot. And this paper from Google was released just this year, right? Generates the entire temporal duration of the video at once. So that's why I think that there's a connection between this paper and this paper. Okay. The second this becomes open source, some dude in his basement will train this on pH. Is that porn? Okay. Yeah, for sure people are going to use this on to generate porn. It's just a matter of time if they're not already doing it already. Okay. So that was that. Now let's go to the second stuff. Okay, so we just went over Sora, which is OpenAI's state-of-the-art video generation model. And now we're going to go to the second part of this battle, which is Gemini 1.5. So Gemini 1.5 was released by Google DeepMind. And this is not a generative video model. It's basically a video, text, and audio understanding model. In their words, it's a highly compute-efficient, multimodal mixture of experts. So multimodal refers to the fact that it can consume multiple modalities, right? Image is one modality, text is a different modality, audio is a different modality. So how is it just using all of those? Well, it's because it's kind of training on all of them interleaved together, right? Once you take an image and turn it into visual patches or visual tokens, you can feed those visual tokens with text tokens, right? So you can feed a bunch of visual tokens, which represent an image, and then a bunch of text tokens, which represent text, and then a bunch of audio tokens, which represent audio, and then more video tokens, which represent, or more image tokens, which represent images, right? So there's no limitation as to what modalities you're using once you turn the raw modality into a sequence of tokens. Then you can basically just feed them into a big transformer and you get reasoning. So this model can reason over 1 million tokens of context and achieves near perfect recall on long context retrieval tasks. Improves state-of-the-art in long document question answering, and so on. Matches or surpasses Gemini Ultra's state-of-the-art performance across a broad set of benchmarks. It has near-perfect retrieval up to at least 10 million tokens, which is a generational leap over existing models. So if Sora was state-of-the-art video generation, GPT is basically state-of-the-art, or Gemini 1.5 is state-of-the-art understanding. So just to give an example, it can consume up to 10 million tokens. So here is an example of what 1 million tokens is compared to the 128K tokens that you're used to in GPT-4 Turbo. So the total amount of tokens that GPT-4 Turbo can consume in any given autoregressive prediction of the next token is 128,000. Right? So it gives you an idea of just how much more information Gemini 1.5 can consume. And not only can it consume that amount of information, but it can also basically leverage all of that information. So what does it mean by that? It means that you can basically feed it the entire Les Miserables by Victor Hugo and then ask it, oh, look at the event in this drawing. What page is this on? And then here's a little image, and this image gets turned into a bunch of patches, then each of those little patches gets encoded into a little visual token, and then those visual tokens that represent this image get concatenated to the visual tokens that represent this question, and then you basically feed it this entire thing. So what the Gemini 1.5 is seeing is it's basically seeing a bajillion tokens representing Les Miserables, and then the very last couple tokens are basically this question. And then the next tokens that it autoregressively predicts is, here you go, this is representing this exact scene in Les Miserables. So it's able to basically find the exact needle in the haystack, right? And that's where the name of this particular benchmark comes from, right? They call this needle in the haystack, which is like an expression in English where, I don't even know where this comes from, but basically a haystack is basically like a big pile of hay, which is like grass that you use to feed animals. And then I guess at some point, someone tried to hide a needle in it. I don't exactly know, but a needle is like the little metal thing that you use to like sew, right? or create clothing. So if you took a needle, that little metal thing, and threw it in a big pile of hay or grass, it would be very, very difficult to find it, right? Almost impossible to find that needle in the haystack. So finding a needle in the haystack is like finding something that's very specific in a very large swath of things. And that's kind of where the name of this particular benchmark comes from, right? You're basically giving it a huge amount of information, a huge amount of tokens, and then asking it to find very specific tokens, right? And the reason something like this is even more impressive is that if you're doing needle in the haystack for just pure text, right? So here's a bunch of text, and then you're asking it, find this exact part of the text, then all it has to really do is it has to really say, okay, here's the text that I want. These are the tokens that represent that text. Somewhere in all these previous tokens, I've already read those tokens. So when you think about what the attention matrix looks like for this entire fucking thing, obviously the things that are here that you're looking for are going to have a very high dot product with the things that you want. So therefore they're going to kind of like appear, and it's going to be easier to kind of like find those exact things. But the reason this is impressive is because this is visual tokens. So here, this image is being transformed into visual tokens, and it's finding the correspondence between these visual tokens and the 2 silver candlesticks, right? Which is, think about this. This is 2 silver candlesticks. It's probably like 4 text tokens, and it's finding 4 text tokens based on a subset, probably only the tokens corresponding to this exact part right here of the image. So very, very impressive stuff here. What else do they tell us? They don't really tell us much about this. Here's the needle, blah, blah, blah. Red is misses, so you're like trying to find things. Sometimes it can't find it. But they do tell us a little bit here. So Gemini 1.5 Pro is trained on multiple 4096 chip pods of Google TPU v4 accelerators. Google's TPU accelerators are basically like their own in-house GPUs that they design. These things are distributed across data centers. We've actually done some streams on the way that they do distribute these. So if you're interested in that kind of pre-training, distributed pre-training, check out those streams. But this is a massive amount of compute, right? This is, nobody has this. The only people that have this are the tech giants. And as I was complaining about before, they don't really tell you what the fuck they trained on. So they say a variety of multimodal and multilingual data. Which is like, all right, it's kind of like we're in a weird place where they're just not telling you what the data is, but the data is the most important part, right? Imagine if nutrition labels imagine if like the companies that make like the super processed food somehow managed to convince the government that they can't tell you what's in the super processed food, because if they told you the ingredients, it would be unsafe and people would be able to then replicate that food. So we're in a weird world now where everybody's just consuming these models and using these models, but we have no idea what the data sets that they're trained on is. And a model is largely just like basically a compression of the data. So it's just a really weird situation right now. Like if I was in the government, the only AI regulation that I would ever put is basically, you have to tell me what you trained on. But the reason I think they don't really want to tell you what they trained on is because they don't want to get sued, right? And much like I was saying that I feel like OpenAI is probably training on video game streams. It's definitely training on Pixar movies. They don't want to say that, because if they say, hey, we trained on all these video game streams, then the people who have those video game streams can come and say like, hey, you need to give me some of that money because you trained on that, right? So I think it's partially existential, partially kind of deceptive, but I just wish they would tell us what they trained on. Okay. So unfortunately, this paper, they don't tell you much. They kind of just continue to show you performance on different benchmarks. This is a nice little interesting graph. It basically shows you that the model is using everything, right? So here, this is kind of like a weird way to demonstrate it, but negative log likelihood, lower is better. So the lower it is, it represents that basically the more the different tokens within that sequence are using each other, right? So this is basically showing you that it's using the entire sequence. It's like looking at all of the tokens that it's consuming in order to find the quote-unquote needle in the haystack. making use of the long context to reduce the model's uncertainty, where the uncertainty is answering the question or producing the next couple tokens in an autoregressive manner. All video clips are sampled at 1 frame per second. Here they're just shitting on GPT-4V. Gemini 1.5 can consume basically entire movies, which they demo here with this, feeding it this 1924 movie by Buster Keaton. The reason they feed it this one is because this is older than copyright, you know? But no one's interested in this, right? Like, we're interested in 2020s movies, so... But they can't show you that because then they could get sued. And look at that, the same thing. So it's able to correlate or find the specific visual tokens of this drawing with the specific visual tokens of this frame of the video. And it has enough OCR that the OCR, which is not even explicit OCR, right? So that the OCR that these vision language models do, OCR is optical character recognition. It's not like it's doing like a bounding box detector and then classifying. That's like old school optical character recognition. New school OCR is just done implicitly via vision language model. So the vision language model is cutting up this frame of the video into a bunch of little patches, encoding those patches, and then it's literally comparing, it's those patches have some equivalent text information, and it's able to basically answer this text information using the visual information, which is pretty fucking crazy. Okay. That's pretty much it. But yeah, this paper is like, look at this. It's literally 58 pages of shit, and they don't tell you anything. It's like the only thing they tell you is like, oh, here's like responsible impact assessment, and here's the performance on blah, blah, blah. It actually is state-of-the-art speech recognition as well. So here they're comparing to Whisper v3. Whisper v3 is the current state-of-the-art speech to text. So it's basically turns a raw audio information, which is a waveform, right? It's like a signal. And to turn that into text tokens, you use something like OpenAI's Whisper. And it seems like Gemini 1.5 is like a little bit marginally better. To me, Whisper is already kind of as good as you could ever want it to be, but they managed to find a little bit extra performance juice to squeeze there. But yeah, most of this paper is just kind of a bunch of crap. It's just a bunch of like benchmarks that no one cares about and safety implications that are imagined. So it's on us as the reader to kind of try to figure out exactly what is going on here and how did they do this. Okay, so one of the first hints that they tell you here, actually, let me pause here. 13-minute, no audio in such an old movie. Yeah, another way to do it. Okay, all right, so as I was saying, so now we're going to try to do some detective work to figure out exactly what the fuck is going on here. So one of the things that they talk about is they talk about a mixture of experts model, right? So that tells you something, right? Because normally, like, they could have used a bunch of different words here to describe. They could have called this a transformer model. They could have called this blah, 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 blah. Like, there's a billion words that they could use to describe this model, but they chose mixture of experts, right? So why that one specifically? And here we have a paper that was released not too long ago, also from Google DeepMind, 13th February 2024, called Mixture of Experts Unlocks Parameter Scaling for Deep RL. Huh, look at that. Compute efficient, right? Compute efficient, parameter efficiency. Look at that. It seems like Mixture of Experts, more parameter scalable models. Okay. In this paper, it's not super important, but basically they use a mixture of experts for the value function. So in reinforcement learning, usually you have this separation between what's called the policy and the value function, or the actor and the critic. Basically, there's a model that determines kind of the value, or for example, if you're doing chess, it'll determine kind of the value of certain positions in a board, right? And if you know about the Q star, right, the Q in Q star refers to this, the Q model, the Q function, the value function. But that's not important. Largely, the only thing that matters in here is that in the 13th of February 2024, Google DeepMind releases a paper where they say, hey, we're getting really good results with soft MOEs. Soft MOEs are a type of mixture of expert. What is a soft MOE? So here you have main differences between sparse and soft MOE. So MOE is mixture of experts. While the router in a sparse MOE, so the way that a mixture of experts model works is that you have a bunch of experts here, expert 1 to n, right? You have a mixture of those. And the way that it's usually implemented inside a transformer is it's basically the experts are here. So the experts are this. You imagine having a bunch of these little MLPs, and then you have a little router network here that basically chooses which MLP to send it to. So that the keyword there is chooses which MLP to send it to, right? So how is it choosing? So one way you could do it is using a sparse mixture of experts. In a sparse mixture of experts, that router network assigns individual input tokens to each of the available slots. So in a sparse MOE, right, the individual token, and here this is an image, right? So the image is broken up into a sequence of these visual tokens. Each one of these little tokens is only being sent to a single expert. So you can see that this expert here is getting a bunch of sky tokens. This expert here is getting the tokens that represent the bill, and the router is choosing which expert to send it to. So that's sparse MOE. Soft MOE, each slot is the result of a different weighted average of all the input tokens. So in soft MOE, rather than the router giving each expert specific hard assignments of individual tokens, it's basically giving it this weighted average. So you see here, rather than a single token, it's getting this average of a bunch. So it's the token that it's receiving is like a combination, a weighted combination. It's 0.01 times whatever this token is, 0.01 times whatever this token is, 0.01 times whatever this token is, 0.09 times whatever this token is, and so on, right? So, and here they make it look like it's like a combination of these images, but remember that this is not being done in like image space. So even though these are visual tokens, it's really just a bunch of little vectors, and then those little vectors are being added together and combined. So what the experts are consuming here is not little patches of pixels. It's consuming basically a vector, and that vector represents each individual patch. But okay, so far we've this is probably what's happening here. So one of the big things that they did here is probably they used sparse or soft MOEs, and they got good results with that. So how did they get this long context, right? So that's the other big part of this paper. It's like, what the fuck is, like, how are they getting this massive context? So there's another paper that was released here. This is Google DeepMind, 15th of February, 2024. This is a human-inspired reading agent with gist memory of very long context. And you're like, oh, okay, look at that. That's a little interesting. Here's a long context paper coming out at the same time that they released this. So I'm like, okay, let's read into this. Okay, LLM agent system that increases effective context length up to 20x in our experiments. And I'm like, uh-oh, LLM agent system, that doesn't sound pretty good. That sounds like a RAG type approach, right? And that's basically what this is. It's interactively reading long documents, and what this does is it creates gists. So it's a little bit of a bullshit idea, but here it is. So example gisting prompt. For each page, we prompt the LLM to shorten the exact content into a gist or summary. So it says, please shorten the following passage, give me a shortened version, do not explain the reason. So this is one way of getting very, very long inputs, is basically you chunk it, you take the very, very long text, such as Les Miserables, right, which is hundreds of pages. It's 1,382 pages, or 732,000 tokens. You chunk it up into little pages. You get an LLM to summarize each of those into these little mini summaries, and then you feed that little mini summary. So, okay, that's kind of not super hype, right? So is that what they're doing? Are they literally just, like, are they just taking Les Miserables, summarizing it page by page, and then summarizing it again, and then summarizing it again? So every time you perform an inference call on Gemini 1.5, there's like a bajillion, it's basically releasing this like cascade of language model agents that just go through and summarize each page, and then summarize until you finally get to a context length that you can fit in the attention map of a transformer. I don't think so. So I thought that, okay, maybe this is what it is, because they're releasing it at the same time as the other paper, and this is also long context, but the more I read this paper, I was like, there's no fucking way this is it, because this, first of all, would be very disingenuous. Right here, they're making it sound like they've solved the long context problem. It seems like all of the tokens are in context, right? So to that tells me that it can't be this, right? Because this is just too stupid. This is just like, these tokens are not in context. It's basically this like agent type, rag type looking thing where they're actually like summarizing each thing, and then the summaries would be in the context. So I don't actually think this is what's going on, right? I think what's really going on is this. So this is a paper that was released on the 13th of February, 2024. This is from Berkeley, but this guy is not affiliated with Google. I actually looked him up. He's not doing an internship there or anything. But here, world model on million-length video and language with ring attention. Okay, so now we finally have something interesting here. So this guy is known for this ring attention, gradually increases context size from 4K to 1 million tokens. Boom. There it is. Okay. Makes the following contributions. We train one of the largest context size transformers on long video and language sequences. Okay, so boom, look at that. Multimodal. So now we have a multimodal transformer that consumes extremely long context things. Okay, that's sounding a lot like this guy's paper here, this ring attention guy. Okay, new benchmarks in difficult retrieval tasks. Wait a second. That's exactly what we were looking at. And look at this. Needle retrieval, 1 million context model. So this is the exact same fucking benchmark, this needle in the haystack retrieval benchmark with 1 million token context, and it's all green. That's suspiciously similar to what's going on here. 1 million tokens of context. It's actually true context, right? It's not this like weird summary bullshit that they were doing in this DeepMind paper. It's actually true context, and they're doing needle retrieval task. And look at that. It's really good at this type of needle retrieval task, right? Like you can give it 1 hour of YouTube videos and it consumes all those YouTube videos, right? It's breaking that up into little 1 second images and then breaking up each of those images into a little sequence of visual tokens. And then you can ask it questions such as, what vehicle was the person dressed in a T-Rex costume riding? So like randomly in this 1 hour YouTube video compilation, there's a guy riding a motorcycle with a T-Rex costume, and look at that, boom, it gets it. So there you go. So this is what I think the Gemini 1.5 is actually doing. I think what they're doing is they're using ring attention in order to drastically increase the length of the context that they can consume with their multimodal language model. And I think that the fact that you have a ring attention paper coming out that shows exceptional performance on needle in the haystack retrieval and also on multimodal type data sets, I think this has to be it, or some variants of this, right? So ring attention, mass sequence packing, other key features for training on million-length multimodal sequences. Let's look a little bit more in this paper. So ring attention is a technique for scaling up context size arbitrarily without approximations or overheads. They grow the context size from a smaller 4K to a larger 1 million context gradually. So basically, as they're training, they initially train with smaller context, and then they keep increasing the size of the context. So it's almost like kind of a curriculum learning approach where the curriculum progressively gets harder and harder and harder over the course of training. In this case, harder is defined by the length of the context. Training on the mixture of video, image, and text is crucial for optimal performance, right? So this is the exact type of multimodality that is seen in the Google paper, right? Where you're basically interleaving the text and the vision tokens, right? You're consuming these text tokens, and then you're consuming vision tokens, and you're answering questions about text tokens. So that's the same type of multimodality that you see here. We implement an efficient masked sequence packing to effectively train with different sequence lengths. I think there's another cool thing. Training on progressively increasing sequence length data with ring attention and modifying positional encoding parameters to account for longer sequence length. So these positional encoding parameters, these are the parameters that get added to each of these, right? So if you remember, when we turn an image into a patch, we have to add these little position embeddings. So the same thing happens with everything, right? So anytime, even with text, right? Each of those little text tokens has a little position encoding added to it as well. I think there's another thing here. In order to distinguish between modalities when generating as well as knowing when to switch, we introduce mechanisms to mark the end of text generation and the beginning of video generation, and vice versa. So at the end of vision, we introduce new tokens, end of file and end of video. So this is how they're weaving them together. So basically, you have these new tokens, such as vision/vision, that let the model know when the tokens have changed. So if we're going back to our Google paper, right, what would this actually look like? It would be start of text, and then all the text tokens associated with Les Miserables, then end of text, and then start of text, and then all the text tokens associated with this little thing here, and then end of text, and then start of image, and then all the vision tokens associated with this, and then end of image, and then start of text, and then it would start just creating these tokens autoregressively. So that's how they're doing this. That's how they're weaving together these different modalities. They're basically creating these new tokens that let the model know explicitly when it's no longer seeing text tokens and when it's seeing vision tokens, and when it's no longer seeing vision tokens and when it's now seeing audio tokens, right? Okay. So maybe what is ring attention, right? So ring attention is this same guy here, Hao Liu. This is the guy who released this paper, which I suspect is the type of stuff that's coming in there. And Hao Liu, in this paper, this stuff is pretty gnarly, but basically what ring attention does is it uses a ring of hosts. So hosts here, think of it like one GPU. So a ring of hosts would be like a setup where you have multiple GPUs. So for example, in this case, you have like 8 GPUs inside a server box, right? So that's a very common setup that you have, where these server boxes that people use in these data centers, they don't just have one GPU per computer. They have multiple GPUs per computer, right? So the ring of hosts here is basically the different GPUs inside that single server box. Each host holds one query block, and key value blocks traverse through a ring of hosts for attention and feed-forward computations in a block-by-block fashion. As we compute attention, each host sends a key value block to the next host while receives a key value block from the preceding host. So it's basically like shuffling the key and the value cache around and then computing all the... So it doesn't get rid of the computational complexity of the attention mechanism in a transformer. What it does is it basically calculates it chunk by chunk, right? So it's still just a transformer consuming a giant-ass sequence, and it's still doing a O of n squared attention on that sequence, but it basically does this little like ring around the rosy of GPUs that are all connected to the same server, such that you kind of almost get like infinite context. And I thought this was kind of just a cool terminology here. TPU torus topology. that just sounds awesome. You know, I almost want to create a little business card that says TPU torus topologist. Okay, but this is the actual algorithm if you want a little bit more concrete about what the fuck is actually going on. So you have your input sequence X, which is going to be your tokens, right? It can be image token or vision tokens, text tokens, audio tokens. Number of hosts NH, this is basically the GPUs that are all hopefully close together, because if they're very far apart, then it's going to be annoying to send stuff back and forth. You're going to split the sequence into NH blocks, right? Where you have one block per host. Each host has one input block. For each transformer layer, you're going to basically compute the attention for every block or for every host. Then you're going to send the key and the value blocks, aka your KV cache, to the next host and receive the new KV cache, and then basically compute the attention with the current subsequence, right? The annoying part of this, though, is that transformers, you have to get through the whole layer before you get to the next block. So transformers, right, they're basically stacks of these transformer blocks, right? But you can't compute this next attention block until you have all the information from this previous block, right? So that's why there's a little bit of annoying here, where you have to basically go through each transformer layer kind of sequentially. So here's the attention mechanism. So this part here is the attention, which is this green brick. And then this part here, for each host concurrently compute memory efficient feed forward using a local attention output. So this second for loop here is this blue part here, right? So that's basically ring attention. And that largely concludes the Gemini paper. So, right, we've basically now looked at Gemini 1.5. It's a state-of-the-art recall, state-of-the-art context length. Okay, they don't really tell you what they're doing, but they give you a hint that it's a mixture of experts. We know that they released a paper about mixture of experts for deep reinforcement learning about the same time. This mixture of experts in reinforcement learning talks about how the big important thing here is soft mixture of experts. So we know that what's probably going on here, it's a soft mixture of experts. Then they release this red herring here. This paper basically is some kind of like rag bullshit. I don't think it's this, but I think it's this. So this is, I think, the other half of Gemini 1.5 is basically some kind of ring attention, just because the similarities here are too much, right? The multimodality of this, the fact that it also gets very good score on this needle retrieval. So what do I think Gemini 1.5 is? It's basically this ring attention, except here, you see here where it says compute memory efficient feed forward using local attention output. Rather than this loop here, replace that with a mixture of experts, a soft mixture of experts, and that is Gemini 1.5. Right, so the soft mixture of experts is usually done here with you have multiple of these MLP. So rather than doing this just single feed forward with a single feed forward block, imagine there's like a for each host do route into the proper expert, and then there you go. Ring attention with soft mixture of experts. And I think that's pretty much it, guys. Let me see if you guys have any questions here. Thanks. Minsuk and Majetti. Minsuk, $50, dude. You need something better to do with your money, man. But I appreciate it. YouTube short this long context rant. I think they use Google's TPU in the world model paper too. Yeah, they do mention it. So inside this one, world model on million length context, they do mention using the TPU as well. So where is it? I think it's here. No, it's here. Here. No, here. Dude, what am I doing? What am I missing? I think it's in this paper. Yeah, here we go. This is kind of interesting. TPU V, these are the different versions of TPU. So TPU V4, TPU V5E, and this is the bandwidth, interconnect bandwidth, right? So something like ring attention, because you're doing it with a bunch of hosts, right? The interconnect speed, the speed at which those individual little host GPUs can send information to each other is very important, right? If it's very slow to send information back between these little hosts, right? Because they're sending each other their key and value blocks, you want something that is a very fast interconnect bandwidth. So compare the TPU V4. Wow, why is that worse? That doesn't make any sense. What the fuck? TPU V5E is worse than TPU V4? It's probably just smaller. That's probably what it is. I bet you the E probably stands for like efficient or something like that, like energy efficiency. So it's probably just... But yeah, I don't know. It kind of makes sense now that they said that they trained on TPU V4 accelerators, right? Because who's going to want to train on TPU V5s if they're literally worse? I don't understand that. Okay. Could they also do this with one GPU, but it would take longer? Probably. It would be really weird to do this with one GPU because you would need to load all this stuff in and out of memory, right? So basically, rather than passing stuff between the GPUs, you would have to basically cache each key value block and then compute and then cache and then compute and then cache. So like you could probably do this, but it would just be extremely slow because this for loop here, you would basically have to be like loading stuff in and out of the CPU memory, the RAM, and then putting it into the VRAM. Any idea as to how they're going to solve the physics problem? physics in terms of this one, you just wait. So they're never going to actually solve. There's no like solving here, right? Like the way that AI and machine learning works, it's like we don't actually know what the fuck we're doing. We're just like, we just like try to 10x things. So it's like, we don't know what to do. What do we do? 10x the model. Okay, 10x the data set. Okay, clean the data set. Okay. So it's like, it's really not, we're not limited by like someone coming up with some interesting new idea. It's like the AI machine learning field is limited by just the scale. So what do we have to do to solve the physics problem? We just have to wait. Just wait another year and they'll train this on 10 times more data and it'll be 10 times bigger and it'll work better. Sora is similar to Walt. I don't know what Walt is. Well, things like dropping balls, sure, I totally get the idea of not being it, but it's kind of tricky to get videos that have physical constraints. Yeah. Spyro, I don't really get how ring attention makes the context longer without increasing the entropy of the answer. So, I guess what you're saying there is that the longer your sequence is, the more possible different tokens in that sequence that you could kind of pay attention to then impact your next token when you're autoregressively predicting it. So you're kind of saying from an intuitive sense, the longer the sequence, the less sure, the more uncertain you're going to be about your next token because there's just so many other tokens that could influence it. Is that kind of what you're saying? But yeah, I mean, they do show here, we don't even know that they're using ring attention. So like, I'm just guessing that they're using something like ring attention. And I bet you it's not even exactly ring attention, right? Like the exact implementation that they use is probably not ring attention. They're probably doing their own kind of secret sauce. I just suspect it's kind of similar to that, but they do show here, right, that you do get, in their model at least, which I am only guessing does something like ring attention, it does seem like as you give it more tokens, it becomes more certain about its prediction. So yeah, I don't know. This is just like some black box situation, right? It's kind of like anything else in AI ML where it's like the easiest way to understand this is just to anthropomorphize and say it's getting smarter because it's smarter. Even with flesh brains, we take 10 years to solve physics for engineering. I mean, we have pretty good physics models, right? Like in video games, like the physics that is in video games is basically like Newtonian physics, right? It's basically like you have things that have mass and the acceleration and the force are related to the mass, and then you basically push things around. And the hard part about physics now is that we don't really have good models for friction and then kind of elasticity, things like that are much more difficult to compute. So like one of the classic issues with the physics engines today is that if you have two objects, right, the way that they overlap is used to usually calculate the force, but then that's how you end up with in video games when you like touch something and then it just like flies out. It's because it overlapped, and then the force that resulted from that decided, okay, well, actually, these two objects are very rigid, and when they overlap, they should be pushing apart with an extremely large force, and then in that way, that's how you get objects that just kind of like fly out in video games. So, and also friction. So, like, if you would do any kind of like robotic stuff in simulation, like the friction between the feet and the floor, or the friction between the grippers and the objects, that's also not very great in today's physics engines. But physics engines that we have are pretty good, you know, especially if you, there's ways to like numerically approximate like friction and all these other things like that so that you can get very nice physics simulations, such as in like, in any kind of Hollywood movie, when you see like those scenes where the whole city kind of like crumbles or explodes or something like that, that's a physics simulation. And that's using explicit equations that were basically created by Newton. But there is no physics here, right? This is just implicit. It's like inside the weights of this neural net, there is some weird black box function that understands the idea that like, oh, when the little flipper of the whale goes through water, the water is pushing up against the flipper of the whale, which is why the very tip of it kind of flares out a little bit when it's pushing down on the water like that, right? But there's no explicit physics there. It's basically just learning this weird implicit model of physics just from watching hundreds and hundreds and hundreds, not even hundreds, billions of hours of footage. But going back to the whole synthetic data argument, if some portion of the data that it's been trained on is synthetically created, or aka is video game data, then the physics model that this Sora model has inside of it includes some of the physics of video games, which is not real physics, right? So there's something kind of interesting there. And that also is the case with other things too, right? So think about it this way, like this model has been trained on a huge amount of like drawing as well, right? So like think about like the face, like this person's face right here, right? It's seen a lot of real human faces, but it's also seen a lot of drawn kind of like anime faces. So really the implicit internal model of a human face inside this Sora video model is not like a pure, only real human video data type face. It has like some, it's, you know what I'm saying? There's some small effect by the fact that it's consumed a huge amount of like 2D animation type stuff too. And it's very difficult to talk about these things because it's like everything is fuzzy and it's all black box. But this is why I feel like people should be talking about the data sets that they use, because the data sets is the easiest way to really try to understand what's going on inside that black box. And you know, if they told us, oh, 50% of this was video game data versus 10% of it is video game data versus 1% of it is video game data, then I feel like we could maybe learn something there. I don't know. I'm kind of starting to talk out of my ass here. Mass, force, acceleration are tokenized nature that work well with our flesh brains. I think you could still fine-tune on the frames of an MD simulation and get something that isn't garbage in the next year. It'll probably be close to actually being useful for that. Okay. I don't know. Do you guys have any questions here? I feel like I kind of ran out of stuff to talk about. I'm kind of scrolling here through these. If Sora is actually trained on a bunch of physics simulation footage from game engines, it basically generalized those physics concepts to realistic image generation. Kind of. I mean, that question is hard to answer because you're anthropomorphizing there, right? Where it's like, what does it mean to actually understand physics or generalize physics or have an implicit model of physics, right? Like, those are just words and terms that we use to kind of cope with the fact that we don't actually know what the fuck is going on inside here, right? Really, the only thing it's been trained on is to basically reconstruct images, right? It's basically try to remove the noise from the image such that you get the correct image. Or in this case, try to remove the noise from these latent space-time patches such that you get the original latent space-time patch. There's a Sora video about the breaking glass that looks super trippy. Yeah, there's still a lot of weird trippy shit. I think we showed the kind of person walking and the legs flipping. That was kind of just the weirdest thing. Look at that. You know what's kind of crazy to think about, though, is that right now, we all have pretty good mental models of what physics does because we've lived in the real world. Right? We've spent most of our lives living in the real world. So we have this ability to detect the uncanny valley, right? But when you think about future generations, like think about some kid that's born in the 2050s. This kid that's born in the 2050s lives their entire life inside a VR headset, and everything that they see, like 99% of all the visual information they receive is coming out of some generative model, right? When that kid is 20, 30 years old, they're going to have seen much more generated content than even real physics stuff, right? So it's like, what happens when the majority of humans are basically spending the majority of their lives inside generated worlds where the physics doesn't necessarily match the real world, you know? Could you end up in a situation where like these people have a hard time like grabbing things from the ground, or like when they jump, they like overestimate how much they jump because they've never even jumped in the real world before. I don't know, there's all kinds of like interesting implications once you start thinking about like generations of humans that like live entirely inside these generated worlds. Like, do the generated worlds really want to capture what real physics looks like, or are they going to be basically, are the weird physics models that exist in these worlds just going to become the physics the world models that we end up internalizing? Okay. I'm kind of ranting. All right, let me do this. I know it's only an hour and a half in, but I do want to give you guys your time. Actually, here's another question by Walt. When they train a VAE, do they use specific bits to represent the bottleneck during training? How would you compute the bits that can be used for storage in the bottleneck? So let's do a VAE. So the VAE that I showed you here, this is like possibly the simplest example of a VAE, right? It's this one here, right? I wanted to pick something that was simple, but for example, this is a VQ VAE. So this is the vector quantized VAE, right? So in a VQ VAE, right? Let's open this image in a new tab. Rather than this bottleneck being basically like free, where it can be any vector, you quantize it such that it's like basically there's some specific limited vocabulary or dictionary that these tokens can be mapped into, right? So it's kind of similar to in a language model how like there's like 30,000 possible tokens that it could predict for the next token. In a VQVAE, it's the same kind of idea. You're quantizing or discretizing this embedding space such that it only has certain values. Let me see if I can find one that has the distribution. Yeah, I'm trying to find one that shows you the, yeah, here, this one maybe. So this one a little bit. So image in new tab. This one shows you like another way to think about what's going on here is that what the encoder and the decoder are doing is they're mapping the raw image into this latent space, and the distribution of data here in the image, there's some corresponding distribution of basically embeddings within that manifold, right? So there's some distribution of little points that it could be. So here, for example, you can say, okay, well, I'm trying to think about, where is it? I need one that has a Gaussian. Like this. So you see how here they're calling this the latent distribution, and they're saying, oh, there's some distribution of points here, and then points that are, it's kind of like, it looks like a little Gaussian, right? A Gaussian is parameterized by the center of the Gaussian and the variance, right? So the VA can be doing something like that, where here's noise, so you're feeding in noise, and what you're really predicting is not a pure vector, right? So your encoder is not saying here's the exact vector. What it's really predicting is the mean and the variance of a distribution that if you were to sample from that distribution, you would then get the actual little point in latent space. I don't know if that cleared things up or if it made it even more confusing. Here's the same thing. So here your encoder is basically giving you the mean, the variance, you add some noise, and this via the reparameterization trick allows you to basically push gradients all the way through, right? Because your gradients are coming from here. Your gradients are coming from the fact that you have a reconstruction loss, and you're going all the way back, pushing through all of these. I don't know if that made sense. Yeah, I wouldn't necessarily worry too much about VQ, VAE, Wall. This is like quite old at this point, you know. I think the only thing you really need to know for a VAE is this. This is like the most important part. It's like this, the fact that you're basically creating this bottleneck, you're forcing this encoder and the decoder to compress and only communicate through this tiny bottleneck. The way that I think about it in my head, the analogy is that the encoder and the decoder are like two prisoners that are sitting in two jail cells that are adjacent to each other, and there's a little hole through which they can communicate. But they have to figure out how to communicate through that tiny little hole, so they have to fit only they come up with their own language, which is very compressed, so that they can communicate through that tiny hole. And that's kind of like how I think about that. I don't know, maybe both prisoners are trying to paint a picture or something like that, and this guy's trying to paint the picture based on the descriptions that this guy's giving him. I don't know, the analogy kind of falls apart, but that's mostly the important part. And I don't think this is exactly what they're doing. I don't think they're using a VAE. It kind of sounds like they trained their own kind of VAE that doesn't just encode individual images, it encodes kind of the whole video at once. Okay. Is the image to noise randomized? The noise is randomized. So in a diffusion model, you start from noise, which is random, and then you remove the noise. And then when you're training the diffusion model, you do it the opposite way. So when you're training the diffusion model, you start with actually your true stuff. So it could be your Unreal Engine 4K video, and then you add noise to it. YouTube short the analogy, please. All right. Okay. Let me sip this water. Let me summarize what we just did, and then let me give the final conclusion here. All right. So today, we read or observed two different papers, or two different works. We compared Gemini 1.5 and Sora. So Sora is the new state-of-the-art video generation model created by OpenAI, specifically created by three fellows here, Tim Brooks, Bill Peebles, and this guy here, Aditya Ramesh. So these are Berkeley PhDs known for generative image stuff, such as instruct pics-to-pics, such as DIT, or scalable diffusion models with transformers, and other things such as zero-shot text image generation, hierarchical text conditional image generation with clip latents, and so on. So they got some heavy hitters in the video, or in the text-to-image world, and then they put these people in a room and gave them a bigger GPU budget than anybody, and they gave them a better data set than anybody, and you give them a little bit of time, and they churn out Sora, which is the now state-of-the-art. It's definitely state-of-the-art, so, I mean, I don't need to convince you about that. Compared to Runway, compared to Pika, compared to Stable Video, generates much longer videos. Videos are of higher quality. The motion is higher quality. The realism is higher quality. It's still not 100% there, but we're getting pretty close, you know? They don't tell you much about what happens in this paper. You know, they call it a paper or a technical report, but really it's just kind of like a generic high-level overview. They talk about this idea of turning visual data into patches, which is not a new idea. People have been doing this in the world of vision transformers forever, right? You basically, transformers can only consume a one-dimensional sequence. So in order to feed an image, you need to transform it into a one-dimensional sequence. And in order to consume a video, you need to transform it into a one-dimensional sequence. The way you do that is you turn it into these little patches, you flatten them out, and then you feed them into your transformer. So that's basically what they do. I think that they borrow some ideas from this Google paper, the Lumiere, which was the state-of-the-art video generation paper in the 23rd of January. In this paper, they use the same autoencoders. I think they use pre-trained VAEs, but they basically replace the UNet with this space-time UNet. And I think that's what they do here. I think not only do they replace the UNet, but I think they also train their own encoder-decoder. So I think OpenAI has their own secret sauce, basically VAE, but a VAE that basically does things in these space-time tokens. They also probably have their own UNet. And other than that, they basically just had a way bigger data set and trained it for way longer, but there's really not that much other secret sauce. They do the recaptioning, so using language models to expand on captions, right? Rather than just having a simple caption like this, they expand it to more, so you have more words, more kind of signal to come in, but that's also kind of an old trick. So there's really not any new tricks here that I can see. I think it's just combining all the current good stuff and then just training it for longer and with more data. The other paper that we looked at was this one here. This is Gemini 1.5. This is Google DeepMind's latest work, and it's basically the state-of-the-art multimodal model, but for the purposes of kind of recall and reasoning. So you can basically feed this model up to 3 hours of video, 22 hours of audio, 7 million words, which is over 10 million tokens, and do all these kind of interesting, cool retrieval tasks, where basically you're trying to find very specific things inside this long context. The reason they show this is because other times that people have tried to do long context, they basically fail. They can feed in that long context, but the model just ends up not being able to remember almost any of it. So here they kind of show you that they can even use visual tokens here to recall specific text tokens, which is very impressive. And then they have this picture over and over again. This figure just comes up over and over and over again, and it basically just shows you just how much more context you get in Gemini 1.5 Pro compared to GPT-4. But much like the OpenAI paper, they don't really tell you much about the model itself or much about the data set that was used. So we don't really know exactly what they did to get this kind of breakthrough state-of-the-art performance. I extrapolated a little bit, so I kind of put on my detective hat, and I think that part of this step function improvement comes from soft mixture of experts, guessing based on this DeepMind paper that shows that soft mixture of experts are quite good for value functions, so probably makes sense that it probably works quite well for retrieval as well. Soft MOE is whenever you use a weighted average of tokens that get routed into individual experts as opposed to a hard assignment where individual tokens get assigned to experts. And I also think that the way that they get the long context is probably something similar to this ring attention. This is a ring attention paper not released by Google, but released very similar time. And this paper also has basically all the same parts as this Gemini paper. It has a multimodal model that consumes image tokens and text tokens. It also goes from 4,000 context to 1 million token context, so the same kind of step function improvement in context. And it also uses the same kind of benchmarks, this needle in the haystack task, where you're basically trying to find some very, very specific tokens within a very, very long context, and it does it with near perfect accuracy. So they don't mention it in this paper, but I feel like that's probably what they did. And it sucks for these guys. So this is a random other team in DeepMind that also got very long contexts, but the way that they do very long contexts is by getting LLMs to basically summarize stuff, and then by summarizing shortened version, they like concatenate these shortened versions and then paginate through these, like, I don't know, this is overly complicated. It's like basically just a system where you're sending a bunch, for every inference that someone sends, it would create spawn this whole chain of inferences that would then summarize and then re-summarize, and then it's just not a good design. So sucks for these guys because this research is probably dead, or maybe they'll do something else with it. But I think that this is probably what the Gemini 1.5 paper is doing. And that's pretty much it. So who do I think won, right? Let's get to the bottom line. Like, who won Gemini versus Sora? So I actually, like, this might be controversial, but I actually think Gemini is more transformative. I think like 3 hours of video with like perfect recall like this is a big deal. This is, people are sleeping, but like GPT-4 was the best for so long, and I feel like now it's finally been uncrowned. I feel like this Gemini 1.5 beats it. There's still plenty of other ways to measure the performance of a language model and multimodal models, right? I don't know how well this does on math problems and blah, 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 but just this recall is very impressive, and I was more impressed with this than with the Sora, because there's plenty of other video generation models that use these techniques, but Sora is pretty good. It is state-of-the-art, so it does have that. And then I also think the timing was also very well done. So you gotta give Sam Altman his credit. Like, this guy is like God mode hype man, right? Sam Altman is not technical. He's a business guy. But releasing this right after Google releases the Gemini to kind of control the conversation and control the narrative, that's a master play. Like, Google out here playing checkers, Sam Altman playing chess. So I think the timing and also video generation makes for just a much more appealing demo. You know, like people are much more impressed by like videos and images than they are by something that's kind of like this, right? Where this is much more abstract. It's like hard to really comprehend how this is like going to change your life, versus it's a lot easier to comprehend how this is going to change your life. So even though I feel like the Gemini one is more impressive to me from like a technical standpoint, I think that the timing of the Sora and the fact that it's a just much more visual modality, so it's easier to kind of like post videos and get excited, I think it's a master play by Sam Altman to put it out there, right? But yeah, that's basically it. I think it's hard to, I don't know who wins. Gemini technically more impressive, Sora more impressive from a marketing standpoint, and impressive from OpenAI is just really good at state of the art, right? Where they can basically just get state of the art on a problem that other people have been working on for a year, and they can just make sure to dot all the I's, cross all the T's, and then end up in a better place than everybody else. Let's see. Yeah, it's Gemini more technically impressive, Sora more hype. Yeah, that's a good summary. It's also like both of these things, like if we want to talk about what this does for the future, that's another interesting thing to think about, right? Like, to me, Gemini kills all the RAG shit, right? Like, there's so many startups right now that are doing some kind of RAG, which is retrieval augmented generation, right? Which is this like these very complicated systems where like you basically have LLMs that like find like summarize things or turn it into an embedding and then find other similar things based on that embedding and then chunking up, and then very complicated kind of chain of thought type approaches to like all that shit is going to go away, because if you can just feed all of your stuff into the model every time, you don't need these complicated kind of systems where you have databases that are indexed by embedding and then you're like retrieving things and putting things in and out of context. Like, this is just going to make all of that go away. You know, like up to 7 million words. At some point, when you open up a window and you're talking with an AI, your entire text, every piece of text that you've written, every piece of image, every image that you've ever had created and taken with your cell phone, all of that will just be put into the context. And then you don't need to have this very complicated system of like pulling things out. So I don't know. I feel like just Gemini is going to kill a bunch of startups, or at least the ideas here, because it's going to take some time to roll out. And then also Sora is going to kill a bunch of startups. Not explicitly. I think you're going to have other companies that basically rush to get to this same point. But think about how much money and people are involved in like video creation and 3D creation, which is going to be huge after they release it, because you can basically do generative 3D with this. So I don't know. I'm starting to get a little sloppy here. My wording is becoming bad, but I feel like by the end of 2024, I don't see a world where we've massively disrupted all the current AI startups and all of the entertainment world, which is basically a huge chunk of the world right now. I don't know. That's all I got, guys. It's all trade-offs. We're all just wasting our time. That's the unfortunate. If you want to have a depressing kind of take off, if you want to take something out of this that's a little bit more depressing, is that it doesn't matter what you do. Like, if you're not OpenAI and you're not Google, you're just wasting your time. Like, they're going to get there. They're getting to AGI. They already have AGI, if you think that language models are AGI, but they're going to get to super intelligence pretty shortly here. Like, I think end of 2024, beginning of 2025, we get to a point where you have AI agents that are basically better at humans at every single possible thing. And because the way that AI and ML works, such that scale is so important, I think that ultimately that's going to mean that all the startups are not going to be able to compete. They just can't compete with the scale. So it's a little bit depressing, but I feel like humanity is just sitting here. We're just sitting and waiting until these two companies basically rush to get to ASI, and then hopefully we live in a kind of utopia after that, but it could become a cyberpunk dystopia. But either way, I'll see you there. You're not bullish on Meta? I think Meta is well positioned because they also have the headsets, but they have the headsets, which is the platform, and they have really good models as well, but they don't have their own hardware. I feel like there's something there about the hardware. I don't know. Hard to predict. The coffee's running out. See you there. Yeah, that's kind of what I'm thinking, but I don't know. The problem with this later stream time is that my brain is just not working as well, and I can't give you guys cool details. So anyways, all the notes for this are in this new repo. So I made a new repo called Docs. And so this is the Sora versus Gemini. Tomorrow we're going to be looking at this AI agent. So we're going to do a little stream on a couple different agent papers. It feels like we just did a stream on agent papers, but even more got released. So if you're interested in AI agents and what they're going to do, you can join us for that stream. If not, hopefully you got something out of this. If you didn't get something out of this, hopefully you got some entertainment out of this. And if you didn't get entertainment out of this, I'm sorry. I'm truly, deeply sorry. All right. Thanks, guys. Thanks, 87. Thanks, Spyro. Jax the Ripper, Majetti, Ed, Emily, Every Dream, Raphael. Who else? Steph, Wool, Chinese name I can't say, Heliophobic Dude, Majetti, The Lookerful, more Chinese names I can't pronounce, Aries, Darshan, Ed, thanks, Minsuk, thanks, Majetti again, Every Dream, Day Lee, Amelie, Sikun, Majetti again, and finally, Blessings of Allah, who was the first person to comment. Appreciate it. Thanks, everybody. See you guys later.